Every year, $28 billion is spent on preclinical research that cannot be replicated. Data from a 2016 Nature survey reveals that over 70% of biologists have failed to replicate the published findings of their peers. The scientific method relies on independent verification of facts. Researchers must be able to repeat tests and produce the same outcomes to self-correct and build upon prior data. Yet the majority of life science researchers find this baseline impossible to achieve. This lack of reproducibility lowers the overall effectiveness of scientific output. It stalls progress by forcing subsequent researchers to build on unverified or faulty premises. The resulting loss of time and capital degrades public confidence. When a field struggles to independently verify its own claims, the credibility of all its findings becomes vulnerable. At a 70% failure rate, the very foundation of biological consensus begins to dissolve. This pattern of failure is linked to high methodological variance and a lack of clear definitions within the research community. Various scientific disciplines and institutions use core methodological terms inconsistently, often leading to contradictory interpretations of the same data. Researchers routinely treat four distinct parameters of observation as if they were interchangeable: precision, accuracy, reproducibility, and replicability. Without a consensus definition for these phrases, it is difficult to accurately evaluate the integrity or the limitations of a study. Addressing the financial and scientific waste in the field requires us to dismantle these concepts and redefine their mechanics. Misunderstanding the formal language of observation ensures that an experiment is flawed before the data is even collected. Every scientific observation contains an inherent margin of error. Uncertainties accompany all counts, measurements, and quantification methods. Whether measuring spatial dimensions, testing material qualities, or determining chemical concentration, a degree of uncertainty is a permanent part of the data. The scale of measurement dictates how closely one observation maps to another. From meters down to nanometers, pinpointing closeness becomes easier. We define precision as the degree of measurement closeness that reduces the associated margin of error. Accuracy is a separate metric. It is the proximity of gathered measurements to the objective true value. While uncertainty is a mathematical guarantee, precision and accuracy are independent tools utilized to manage it. This coordinate system maps observations, with the center representing the true value. First scenario: low precision and accuracy. Points are widely dispersed. Second scenario: high precision, low accuracy. Data is tightly grouped, yet skewed away from the true value. This creates a common trap. Researchers often assume closely clustered measurements mean valid data, but a measurement can have poor validity while highly reproducible. This bell curve shows the cluster is statistically sound, yet incorrect. Third scenario: high accuracy, low precision. Points scatter widely but uniformly around the origin. Their average targets the truth. Finally, in the fourth scenario, data points pull together into a tight, dense cluster directly on top of the target. This represents both high precision and high accuracy. Confirming this state requires visual examination of the data's means and standard deviations. Achieving precision without accuracy simply means perfectly repeating an error. Understanding precision and accuracy clarifies individual measurements, but verifying entire studies requires looking at the broader methodology and systems in place. The American Society for Cell Biology defines reproducibility as achieving consistent results using the exact same input variables, protocols, and computational methods. This proves the process is functional. Inputs run through the system a second time, locked in place. Replicability is the process of gathering entirely new data to address the same scientific inquiry and achieving consistent results. Replicability is what proves a hypothesis is robust enough to hold up across different environments. Reproducibility ensures procedural transparency, but it offers no guarantee that the final result is actually correct. If the original input data was compromised or the analysis settings were flawed, it is possible to flawlessly reproduce a false positive. Conflating these terms causes peer review failures. Researchers falsely believe that proving their code works is the same as proving their conclusion is true. This methodological confusion brings us back to the 70% failure rate currently seen in biological research. Biological research is uniquely vulnerable because it relies on a wide diversity of approaches to study chaotic living systems. Within these complex networks, slight, unrecorded shifts in methodology cause experimental outputs to diverge. When researchers fail to precisely label data and document their specific analysis settings, computational replication completeness becomes impossible. In systems as intricate as cellular biology, the transparency of the procedure is more critical than any single isolated conclusion. Combating the reproducibility problem requires the adoption of open science, a framework built on total methodological transparency. Open science demands comprehensive, impartial explanations of every technique used to acquire and process data, making it simple for outside observers to access and audit. Implementing this standard requires a shift in professional incentives, directed by publishers, funding organizations, and politicians. These institutions must prioritize computational replicability and precise documentation over the pursuit of novel or flashy results. Scientific reporting succeeds when it provides an unbroken, verifiable map of how an answer was generated, making the final conclusion secondary to the process used to reach it. Without a verifiable, meticulously documented methodology, experimental data is scientifically indistinguishable from noise.